In part 5 of our lesson on applications of vectors, you will learn how to solve problems involving the equilibrant. The equilibrant is just the opposite vector of the resultant. Now recall that opposite vectors have the same magnitude but opposite direction. We've learned previously what the resultant is. Remember, the resultant is the resulting vector that occurs when you sum together two vectors. So the equilibrant will just be the opposite vector of that resultant. In this example, we are told that two rescue boats pull a broken down motorboat toward a boathouse with forces of 724 pounds and 875 pounds. The angle between the two forces is 21.7 degrees. Well, let's get started making our drawing. We know we have two forces. One of them is 724 pounds. The other is 875 pounds, so a little bit longer. And we know that the angle between those two forces is 21.7 degrees. We are being asked to find the magnitude of the equilibrant and the angle formed between the equilibrant and the 875-pound force. Remember that we just learned that the equilibrant is the opposite vector of the resultant. So we need to sum together these two vectors and find the resultant. Then we can draw in the equilibrant as the opposite vector of that resultant. Because the two initial points of the vectors are together, we know that we are using the method for summing vectors where we create a parallelogram. So let's do that. Opposite the 875, we'll draw a side that is parallel and equal in length. Opposite the 724 side, we will draw in a dotted line that's parallel and equal in length. And we know that the resultant is the diagonal starting from the joined initial points. We have to find the magnitude of the equilibrant, which we know will be the opposite vector of this resultant. And we also have to find the angle between the equilibrant and the 875-pound force. So we will have to find that angle. We need to get some triangles going here, and we know that the diagonal, which is the resultant, divides the parallelogram into two congruent triangles. So we could use either triangle. Doesn't matter if we want to use this one or if we want to use this one. So in this lower triangle, we know the dotted line here is going to be 724. We need an angle in our triangle. Be very careful because the 21.7 degrees is not in any triangle. The 21.7 degrees is the angle of the parallelogram, but we can use the theorem that says that consecutive angles in a parallelogram are supplementary. So that means we can do 180 degrees minus 21.7 degrees to find out that that's going to be 158.3 degrees. And now we know that this angle in our triangle, which is also in the parallelogram, is 158.3 degrees. Remember that these two angles are consecutive angles of the parallelogram, so we knew they were supplementary. That's why we could subtract 21.7 from 180 to find out this angle. Now, as we analyze this triangle, we see that we have side, angle, side, and whenever we have side, angle, side, we know that we can use law of cosines. So we will be able to solve for the length of the resultant, and remember that the length of the resultant is the magnitude of r. So now the magnitude of r squared is going to equal 875 squared plus 724 squared minus 2 times 875 times 724 times the cosine of 158.3 degrees. Because we had the magnitude of r by itself over here, we had to have its opposite angle as the bookend. So let's grab our calculators. We know that the magnitude of r will then be the square root. Let's add these two together. 875 squared plus 724 squared is going to be 1,289,801 minus 2 times 875 times 724 is going to be 1,267,000. And then we have to take that times cosine of 158.3 degrees. So let's calculate this number now to find out the magnitude of vector r. We'll hit second square root 1,289,801 minus 1,267,000 times the cosine of 158.3, close the parenthesis, enter. And rounding to the tenths place, we get 1,570.7, and the units of force in this problem are pounds. Now that is the magnitude of the resultant, so let's go ahead and label that in our picture. We know this is 1570.7. Now, because the equilibrant is just the opposite vector of the resultant, we know that means that their magnitudes are equal. So then that means the magnitude of the equilibrant is going to equal 1,570.7 pounds. And we can put that on our picture. Now, to help you understand what the equilibrant is, that would be the force required to hold the broken down boat in place against the two rescue boats. So, in other words, remember that this point right here is where the broken down boat is. And if one of the rescue boats is pulling in this direction with a force of 724, and the other rescue boat is pulling in this direction with a force of 875, the broken down boat would travel along the path of the resultant. Now, if we wanted to counteract that, then we would have to have, say, a third boat pulling in this direction, the direction of the equilibrant, with a force of 1,570.7 pounds. Now, we also had to find this angle, theta, which was the angle formed between the equilibrant and the 875-pound force. Now, theta is not inside any triangle, but we could go ahead and find this angle. Maybe we'll call it alpha. We know that alpha and theta are a linear pair. So once we know alpha, we could subtract from 180 to find theta, because alpha and theta are supplementary. Now, an important fact to notice about alpha is that we know it will be acute since our triangle already has one obtuse angle in it. So now we can use law of sines to find alpha. And the sine of alpha divided by its opposite side, which is 724, is going to have to equal the sine of 158.3 degrees divided by its opposite side, which is 1,570.7. Cross multiplying, we get that the sine of alpha is equal to 724 times the sine of 158.3 degrees divided by 1570.7. We can enter that number into our calculators. 724 times the sine of 158.3 divided by 1,570.7, we get 0.17043, etc. And let's go ahead and store that in a memory location, maybe A. We know that we'll take the sine inverse of both sides. So on the left-hand side, we have the sine inverse of the sine of alpha. On the right-hand side, we will have the sine inverse of this number that we just stored in A, 0.17043, etc. Solving for alpha, we have to do the sine inverse of memory variable A, and we find out that alpha is 9.8 degrees, rounded to the 10th place. So if we put that in our picture, we know that because theta and alpha are a linear pair, they're going to be supplementary to each other. So theta is going to equal 180 degrees minus 9.8 degrees. We enter that in our calculators. 180 minus 9.8, and we find out that theta is equal to 170.2 degrees. In this example, we are told that two forces act upon the same point. So let's make a point. One of the forces is 113 pounds, and the second force is 221 pounds. Now, looking ahead in the problem, we can see that we are not given the angle between the two forces. In fact, that's what we are going to have to find. So you don't really know what angle to make between the forces, so we're just going to draw a generic picture here. We'll put our first force at 113 pounds here. And our second force, we don't really know what angle to put between the forces, but we do know that since the second force is 221 pounds, we should make its vector about twice as long as the first vector. So this will be the 221 pound force. Since these two vectors have their initial points together, we know we're going to be using the method where we make the parallelogram. So let's go ahead and dot in the opposite sides that have to be parallel and equal in length. And we know the resultant will be the diagonal of the parallelogram starting from the same initial points there. So we can label this vector R. Next, we are given that the magnitude of the equilibrant, so let's write this down. The magnitude of the equilibrant is 289 pounds. Now, if we add that to our diagram, we know that the equilibrant is the opposite vector of the resultant. We know its magnitude is 289. Now, because the equilibrant and the resultant are opposite vectors, we know that their magnitudes are the same, they just go in opposite directions. So we know that 289 is also going to have to be the magnitude of the resultant, and we can add that into our picture. We are being asked to find the angle between those two forces. So let's call this theta. The diagonal of the parallelogram divided the parallelogram into two congruent triangles, so we can pick one of them to work on, maybe this lower one, and we'll label this dotted line with 113. Now we notice that theta is not in either of our triangles, but we can use an angle of our triangle that is also in the parallelogram, and that would be this angle right here. Let's call this alpha. Now to find alpha, we analyze our triangle and see that we are given side, 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 which means we can use the law of cosines. Since alpha is the angle we are solving for, we know that its opposite side, which is this 289, is going to be the side that's isolated. So our equation will be 289 squared is equal to 221 squared plus 113 squared minus 2 times 221 times 113 cosine alpha. So let's go ahead and start finding some of these values. 289 squared is 83,521. If we go ahead and add these two squares together, we have 221 squared plus 113 squared, and we get 61,610. We will subtract. Let's go ahead and do this product. 2 times 221 times 113, and we get 49,946. That has to multiply the cosine of alpha. So we're working to isolate this cosine of alpha. So first, let's subtract 61,610 from both sides. So we will take the 83,521 and subtract 61,610 and get 21,911 has to equal negative 49,946 cosine alpha. Next, we will divide by the negative 49,946. So the left-hand side becomes negative 21,911 over 49,946. And the right-hand side is cosine alpha. We have to take the cosine inverse of both sides. So the left-hand side becomes cosine inverse of negative 21,911 divided by 49,946. And that has to equal the cosine inverse of the cosine of alpha. The right-hand side will simplify to alpha, and on the left-hand side, we grab our calculators and do second cosine inverse of negative 21,911 divided by 49,946. And rounding to the 10th place, we see that alpha is going to be 116.0 degrees. Now that's not the answer to the question. Remember, the question wanted us to find theta here. But let's get alpha in our picture. We see that alpha is equal to 116.0 degrees. Now to find theta, remember that theta is this angle in the parallelogram between the 113-pound force and the 221-pound force. And theta and alpha are consecutive angles in the parallelogram. Now we have a theorem that says consecutive angles in a parallelogram are supplementary. So that means then that theta is going to equal 180 degrees minus 116.0 degrees. And we see that theta then is going to be 64.0 degrees. And that is the angle between our two forces.